So we are going to start the next session on AI in games. So as you know, AI has been applied in many domains, but a game is one of the very exciting domain. And our first speaker, Long Lin, is director of AI at Electronic Arts. And I have known Long for many years, since when he joined eBay data science team. And he later joined Walmart Lab as a worked there as a director of engineering. So let's help welcome Long.
So, which is the okay, cool. Oops, sorry. Okay. Thank you, Julian. It's a great pleasure to be here and glad to see so many people are interested in AI. Today, I'm going to talk about AI applications in gaming, especially the scope of work we are working on at EA. So, EA is a gaming company. It produces some of the most popular games like FIFA, Madden, Battlefield, etc. Besides a set of popular games, EA also provides 24/7 live services that support all the gameplay. It also has the core play engine and technology platform that being used by the game studios around the globe. As part of the technology platform, it's our job to make the future of gaming possible. So our CTO can describe a picture of the future gaming. At EA, we envision the future in which games go even beyond the immersive experience players enjoy today. I'm talking about games that offer living, breathing worlds that constantly evolve. Imagine such an open world games that thousands of players play in the same battle, interacting with each other. How do we make this happen? How do we create a world that is huge? And how do we create the content that is personalized to each player's interests? And how do we create human-like NPCs? And most importantly, how do we make sure that we deliver great experience for our players? As the game becomes more and more complex, all of these won't be feasible without the use of AI. At EA, we leverage AI everywhere across the entire life cycle of our business, from game creation to gameplay to game operation. Today, I will focus on one of the use cases, AI agent and simulation. Now, let's back up a little bit. There has been a lot of breakthroughs in AI in the gaming field. IBM Deep Blue was the first AI agent that beat the best human players in chess. Google DeepMind proves that with combination of deep neural network and Monte Carlo tree search, it can train an AI agent that plays the game of Go at superhuman level. And more recently, OpenAI shows that AI agent can play the game of Dota at superhuman level and can cooperate with other agents like professionals. But crushing human players is not the only goal of AI in games. Can we also create AI agents that play the game similar to human players? Can we also leverage AI to benefit games? Both answers are yes. And one might ask, why so many breakthroughs happen in the gaming? So games, especially video games, are one of the best playgrounds for AI applications. There's a lot of human interaction to produce data, to test hypotheses, and to measure the performance. And it's all virtual, which means fast iteration, and it's okay to make mistakes. And most of games are well scoped, and one can further refine the scope to a simple problem to solve. And it is relatively easy to generate and use the data. This is particularly true for people who are working in the gaming industry. And for games, the state action and rewards are relatively clear, and the result is measurable, and most of the times can be visualized. In order to provide the best experience to our players, game designer usually conduct play-testing, but solely rely on human test players might not scale. AI agent can play the game much faster than human being, and can explore the game states more efficiently. Agent can learn to play the game with different goals, like train a human-like NPC, simulation of the gameplay, exploration of the game space, help with the game design and game balancing, find the optimal solution like AlphaGo or OpenAI 5, provide fast test and feedback loops, and find potential defects in the games. So this is one example of AI agent using games. So as you can see in this video, we deploy AI agent to the Sims mobile game, which is a popular mobile game, and we deploy to a dev-built version of the game. AI agent is thousands of times more efficient than human players. It provides near real-time feedback loop through the metrics it collects around the gameplay. And we can deploy as many agents as we want to provide insight to the game designers. It can help answer all these questions, like, is there a significant imbalance in the relationship categories? How many actions are needed to progress in each of the careers? How do objects impact career progress, and how much impact did the build change actually make? All of these insights will help the game designer better fine-tune the game and provide better experience to our players. So most AI agent problems can be formulated as Markov decision process. This is a nice picture from David Silver that describes the workflow of the Markov decision process. Agents start from observing a state from the environment. Then it decides to take action, then move to the next state. Along the way, it collects some of the rewards. So given this setup, the goal is to find a policy, pi, that given the state S, to decide what is the action to take to maximize the cumulative gain. But more oftenly, the agents are dealing with incomplete observation of the game state. This is called partially observable Markov decision process. And this describes a lot of problems we are trying to solve at EA. AI agent can be difficult to train. The state space might be large, especially for the modern games. The action space can also be large. And for games, they might take millions of ticks to complete, which result in a large number of steps in the game episodes. The rewards can be sparse and compressed. An agent can take simultaneous actions at the same step. And multi-agent can interact with each other, cooperating or conflicting on the same task. And last but not least, agent will always learn what you teach it to learn. So designing the proper reward function is critical. This is particularly true for the games that long-term strategy is important. Luckily, with advancement in computing power and AI computing, large-scale neural network and deep reinforcement learning become possible. We can always distribute our computations, distribute our data to speed up our training process. And we have far more data than before. We have more tools, libraries, and frameworks to leverage, like TensorFlow, Dopamine, OpenAI, Dreams, and Universe, DeepMind Lab, etc. But those libraries, they usually don't have access to the game environment. So they start from the scratch, frame buffer. And the action space are usually joystick moves and button clicks. Given that we have certain access to the game environment, we might not always start from the frame buffer. Although the frame buffer approach is like the future direction, and it marks some of the greatest breakthrough in AI history. But we can choose to start from something at a higher abstract level, like game state parameter, like abstract actions. And scope of the problem can also be well defined. Splitting the game state space and action space into hierarchies of simple problem has seemed promising and efficient in the real life use cases. And we can always leverage the player data. We have tons of player data to leverage to speed up the training process, to better train our policy through demonstration or imitation learning. Most of recent impressive AI breakthroughs are partly due to improvement in the computing power and AI computing. There's an analysis by OpenAI saying that the amount of compute being leveraged by the largest AI application training process has doubled every 3 to 4 months in the past 6 years. It is exponentially growth. And for complex games, it might take agent hundreds of thousands or even millions of iterations to reach a human player level. The cost associated with these approaches might be too high to justify the benefit of many AI applications. At EA, we trained the AI agent to play modern games, especially during the multiple steps in the game development cycle. We want to train a reusable agent that can adapt through multiple development phases and multiple builds of the game with reasonable cost and within reasonable time frame. So as I mentioned before, we don't always start from the frame buffer. We build a game environment which encapsulates the game logic and provide the information which is observable and available to the human players, like how much resource do you have, how many buildings, what's the status of nearby players. And we build a universal interface between the gameplay environment and the AI agent learning environment where agent is trained and executed. This approach has shown promising in a lot of applications and improve the efficiency of the training process. When talk about Markov decision process, the first approach comes in mind as usually reinforcement learning. It's the mainstream methodology to solve this kind of problem. Reinforcement learning is a machine learning techniques that learn from repeated behavior of the agent itself, learn from trials, errors, and rewards. It's like training a puppy. The more of the positive behavior it performs, the more reward it gets. The more of the negative behavior it performs, the less reward it gets. So oftentimes, the puppy will learn to perform more of the positive behavior and less of the negative behavior. The same process applies to the reinforcement learning. At first, we have an initial policy, and we just deploy the policy to any games. I will use a race car game as an example. The agent will play the game, and then there might be some successful trials or failure trials. Over time, the agent will learn to perform more of the actions that lead to successful trials and less of the action that lead to failure trials. At the end of each episode, we collect the state action pair along with the reward, and we use those information to update our policy. And this loop continues until it converges. And in hope of arrive at a generalized policy, neural network is oftentimes being used. As the game gets complex, the neural network might need to be deep. That means a couple hidden layers might not be enough to capture the complexity of the knowledge. And of course, one can use any function approximator to train their models. So to recap, reinforcement learning learns from rewards, trials, and errors. And the goal is to find the optimal solution. It can explore the world beyond the scale of experts and train the agent be able to play the game in the superhuman level. It provides a fast simulation and iteration. But there's complexity around this approach, especially for the non-frame buffer approach. How do we represent the knowledge base around the environment? How do we represent the game state, action state, and the reward functions? This is particularly true when we try to deal the work in the non-frame buffer space. And the efficiency in transfer the data into the well-performed policy is highly depends on how efficient you can represent this knowledge. And even for the frame buffer approach, define a proper reward function is critical. And we can use some help to overcome those kind of complexities. Another approach we leverage is imitation learning. Imitation learning is a supervised learning approach. It usually works like this. You are given a set of demonstration data from the players. I will continue to use the race car game as an example. Our goal is to train a policy that have similar behaviors as the demonstrators. From the demonstration data, we can get a set of state and action pair. And then we can train the policy based on that training data set with the goal of creating a policy that mimic the behavior of demonstrators. And again, based on the complexity of the game, neural network or deep neural network are oftentimes being used. So imitation learning learns from the expert demonstration with the goal to arrive at human-like behaviors. It's simple, efficient, works well at a state space where we have a lot of demonstration data coverage. And it's great at picking up styles for a certain player or set of players. But it might not perform well when the state space coverage is limited of the expert data. This can be overcome by providing a lot of training data, but again, this is also limited by the speed and scale human player can generate the data. And sometimes there might be no long-term planning for the imitation learning. Imitation learning has been widely used in training the self-driving car, and it also shows promising results in training the AI agent playing the games. Also, imitation learning can be a great help for the reinforcement learning. It can establish a good baseline for the reinforcement learning, and we can use the policy that generate from the imitation learning to start our reinforcement learning to increase the chance of the policy converge. Also, the data from imitation learning can help to explore the game space more efficiently. Now, let's revisit the training flow. We have a game environment that encapsulates the game logic, and we have an AI agent environment where the agent is trained and executed. What are the components needed in the AI agent learning environment? Of course, there need to be a training environment and policy storage. We need to have an agent management system and agent execution engine. Most importantly, we need to build a proper data pipeline that fills the entire training lifecycle. So we have been working on training AI agent to play modern games. We leverage the methodology ranging from multi-resolution Markov models to DeepQ network on a variety of games and a variety of use cases that we discussed earlier in the session. So looking ahead, we'll continue to explore more state-of-art methodologies like policy-based reinforcement learning, which has shown great success. In more complex environment with multi-agent interacting with each other. And we are also researching on distributed training to make our training process more efficient. So this concludes my talk. Thank you.
We have time for a couple of questions. If you have a question, put up your hand and our volunteer will bring the mic to you.
Yeah, great talk. I love it. From a user perspective, a lot of games are basically played on, GPUs.
Yes.
A lot of this inference work you're expecting to do while the game is in play may end up consuming some GPU cycles.
Yes.
So it looks like you know where I'm going. So have you thought about sharing this workload, say, on the CPU side, or figuring out a way for you to continue with the frames per second, right, for the game, so the experience doesn't go away, but at the same time you're leveraging that AI, ML, agent-based play?
Yeah. So great question. So as you mentioned, a lot of games are playing in the GPUs, right? So so for the frame buffer approach, the cost of the communication between the GPU, basically the data from the gameplay environment to the actual environment that agent is training is high. And also, if you think about in terms of speed up the agent training process, you often need to clock your game in a much higher speed. So the time it takes to render the game might be expensive. So that's why, we are still using the frame buffer approach, but for the scenarios that we can abstract certain higher level of information and start from the game state parameter to either to help render the game or power the gameplay logic, we usually start from that. And this is same, so the same logic applied to the action space as well. And we do have some paper published, in some of the conference or journals, and talk about this kind of research effort.
Yeah, hi.
Yeah.
A great talk. My question is, you spoke about imitation learning and reinforcement learning.
Mm-hmm.
I was wondering, have anyone tried using transfer learning? Do you see any application for transfer learning in this game area of the game?
Yeah, so the way I think about it, you can use the transfer learning to get the experience from, for example, between the similar games, like for example, both are the first-person shooting games, and you can definitely use some of the techniques over there. But currently, our main research focus is how to come up with a fast and adaptive approach for cross multiple builds of the game. And in that context, so transfer learning definitely helps, and actually it helps with how we can adapt move our agent from one build to another build, and maybe from one game to another similar game.
All right, let's thank our speaker.
Thank you.
Thank you. Our next speaker is Yuandong Tian, research scientist and manager from Facebook. And he was our actual speaker last year. And this year, he's going to talk about building deep reinforcement learning framework for games.
Thanks everyone for attending the talk. So today I'm going to talk about planning in reinforcement learning. So I made a little bit different in the title to actually reflect the talk better. So First of all, I think we know that AI has been working in a lot of situations, right? So like object recognition, medical imaging, speech recognition, etc. But there's still a lot of things that AI cannot do. For example, how to model common sense, right? So I think people have been trying to make a chatbot and question answering work better. But till now, it turned out to be the case that AI is actually finding the relationships, a very strong correlation between the answer and the question, but not doing the actual reasoning. So this is something that AI should be able to improve. And also, AI cannot deal with very few supervised data, right? So for example, for autonomous driving car, there's a lot of situations that AI cannot have seen before. So in that situation, how could AI deal with the situation that you have, it hadn't been trained beforehand? It's actually very hard. So in order to achieve that, there's a lot of problems we need to think about, right? So if you just use supervised training, so what we actually see is this kind of performance curve, right? So at the beginning, you apply AI into your system, and you put a lot of data there and see, oh, it really works. And you see the curve is going up quite quickly. But however, after you put more and more data there, and you start to have different emotion changes, you might going all the way from a little bit like stressful to all the way to despair, because you find that no matter what kind of data you put, there's no way it doesn't work, and still there's a gap between human level as well as compared to the current the best system level. So in order to make things better, we definitely need like novel algorithms. Okay, so one algorithm that is a good candidate is called reinforcement learning. I think in the last talk, we already seen a definition of reinforcement learning. So here, I don't want to repeat it. So basically, like reinforcement learning is you have an agent that interact with environment so that agent can take the current state and then make the action. And the action will change the environment, and the agent will see the state again. And so basically, you repeat this procedure until the agent has finished an episode or finished a task. And the goal here is trying to maximize the cumulative reward, right? So because of agent is often running in a virtual environment, so this actually makes things much easier because you can generate as many data as you want. And this is actually enable a lot of very strong researchers in that direction to solve problems like Atari games, like Go, like Dota, and also like Quake 3. And for StarCraft, we are seeing like interesting progress there. So, and people may wonder, okay, we have seen progress on all these games. So what will be the next one, right? So people will think about, okay, maybe what is the next? Do we need to build like a more and more complicated environment? Maybe do we need to use a stronger, more and more machine to train the model? It's actually not known. So for now, I think we are in the research community, and we really want to understand, want to think about what is the next step we want to think about, want to do. So here I want to talk about planning. So first will give you an example about why planning is important. So this is an example about AlphaGo 0. So you know that AlphaGo 0 was a paper that is published last year in Nature by DeepMind about how can we train a very strong Go bot that can beat may become superhuman with zero human knowledge. So this looks very incredible because previously people all think we need a human supervision to actually make a very strong bot. So the idea is very simple. So you start from a random, very random models, and you use that model to plan ahead to play the game. Okay, so you start from empty ball, and every step you just find a move that is the optimal move according to the planning procedure that is used, that is using that current model. So you get a lot of self-play data. So once you have a self-play data, you basically put the data into the supervised training procedure, and you output a better model, and use that better model to generate training data again. Okay, so very simple. You just like have keep repeating this loop, and surprisingly, you actually see very strong performance out of that. So there are two 3D version which only use 4.9 million games, can already defeat the AlphaGo Lee, which is basically being used when competing with the world champion Lee Sedol in 2016. And their 40 days version is even stronger. Okay, but there's a lot of mysteries there, right? So people may wonder, okay, why this simple algorithm actually works. So in order to replicate their approach, and we want to understand what's going on, we actually use ELF platform to try to replicate this kind of algorithm and want to understand what is going on in these mysteries for loops. So this is a paper that published last year in NIPS about an extensive, lightweight, and flexible framework for game research. And the code is online, and if people want to use it, they can go to this one and go to the next link that is actually an updated version of it. So ELF is very simple. You just put all the dirty things into C++, and we open a Python interface. And this interface, you basically replicate the initial for loop in the reinforcement learning, rather than think about all the detailed stuff in the C++ side, which requires multi-threading or communication stuff. So that's basically a conceptual, simple framework. And this is like one slide showing how ELF works. So you have a few game threads running at the same time. And from time to time, they want to call neural network to get the next action and next policy, right? Or get the current value. So, but this call needs to be batched, because the neural network usually is much more efficient if you batch things together. So ELF is basically a platform that can do dynamic batching on different threads. So this is basically like one-sentence summarization of how ELF works. So we improve on this existing approach by setting up a distributed version of ELF. And then you can basically put in both AlphaGo 0 and Alpha 0, which is a successor of AlphaGo 0 that use a synchronized version of training together into the same framework. And you can basically like enable, disable these two by a few switches. So with this framework, we was able to replicate their performance in a comparable manner. So we train our system using 2,000 GPUs in 2 weeks. Maybe we can actually train it less than 2 weeks. We are trying to do that again. And we actually have decent performance against professional players. And we actually open source the code as well as the pre-trained model for the Go and the machine learning community. So I think the current model of OpenGo is the best open source Go model in the world, and everyone can use it. So here's like a few summarization performance. So you see that we actually collaborate with the Korean professional Korean Go Association. And they basically have 4 professional players. They are all very high rank in the world ranking. And we use our OpenGo program to compete with them. And so each of the Go player is assigned to offer, they can use unlimited thinking time to think about the next move. And on our side, we only use single GPU, and every move is only using 50 seconds. And it turned out that they cannot beat us in a single game out of 20 games. So we also have other comparison with a different version of replication of AlphaGo 0, which one is the Lila 0. So the interesting thing is not only the replication, but also we were able to see how this kind of system works, right? So this is actually something that is more important from the research side. So first of all, what we actually see is, if you start from scratch, you start from this training, at the beginning, everything is random, so you don't expect to see anything interesting there. But the meaningful moves actually come from the end of the game, right? So because at the end of the game, you really have the reward signal, which tells you who is winning the game. So this is very important, and you basically use that information to backpropagate. Backup, I would say backup. It's different from the backpropagation of the neural network. It's from all the way to the beginning opening of the game. So this is very interesting. And you can see the boss is already very strong, even it played random moves at the beginning. So this is interesting. And the second thing is we actually find that planning is actually how the new knowledge is created. So if you put if you already have a trained bot, and you use that trained bot to play against a bot, but without training, without planning, right? So you have a bot that has equipped with the planning, and you have a bot that has no planning there, and you will see as long as the planning, you have, for example, several hundreds of rollouts for the planning bot, then that bot is very, very strong compared to the unplanned bot. And the training is actually using this kind of structure to extract knowledge from the planning. So the planning may say, OK, that move is better. OK, then after that, neural network will try to remember that move is better than other moves. And because it remembers a lot of important moves and also a lot of situations in which black may win or white may win, in the next situation, you can use that as the basis of planning and to plan farther ahead. So that's basically the reason why it works. So this is actually happening in other different places as well. For example, if you actually do a temporal difference learning in reinforcement learning, you actually do the same thing. You do a one-step or T-step or different kind of planning all the way to the next, so that you actually get information from the planning and can try to extract information and save them into the neural network. So this is actually ubiquitous in different situations in reinforcement learning. And you also see how the game AI is created. People have to also use planning to do that. Okay, so moving forward, okay, we already have a ground truth dynamics model, right? So we already know that the rule of the game of Go, right? We basically know we can get a lot of data from self-play or from a random sampling of the states. But what happens if you don't really have a ground truth dynamic model? This is actually very, very common. Yeah, for example, if you really want to operate on robots, and the robot may have a dynamic model that is very hard to get, right? So this is one thing. And the other, maybe there's only human or expert trajectories. There's no world model on top of that. For example, you want to play games by watching other people playing games. So you basically see the video sequence, but you don't really know what action they take to achieve that video sequence, right? And also, there could be situations that it's very expensive to get the full model. Maybe in self-driving car, it's very hard to build a simulator because simulator may always have issues. So in that case, how can we train it? So the question is, the answer is very easy, right? You just want to train a model on top of that. So here I'm going to talk about two recent works that we have been trying about how to build a model or how to use reinforcement learning to improve a plan. So this is basically the rest of the talk. So the first part is how can we build a model to help navigation of an agent in a virtual environment. So here you have a virtual environment, and you have an agent that can move around. And the goal for the agent is trying to move to some places, right? So here the solution for our paper is we can try to build a semantic model on top of all the abstract concept in this virtual environment. Yeah, for example, when this agent is to find a oven, right? It has already known where are the outdoor, where is the living room, and where is the sofa, and they know the relationship between the two. Then you can try to use the relationship to infer the rest of the opponents, the rest of the room, where they are. So you might use a Bayesian network to basically predict the probability that the living room is connected with the kitchen, and etc. And then you can basically use that to do the planning. And the planning will be on this graph, and there will be a much more efficient way of understand the situation of the robots and try to guide the robots to the right place. So basically, we propose what is called a LEAPS. There's a learning and planning environment in planning frameworks that can be used coupled with this semantic models. You start with all the priors of the rooms. This prior can be extracted from the training environment. And then you start to explore the environment. Whenever you explore the environment, you update your prior knowledge so that this prior becomes posterior. So once you have a prior and posterior world model, you can plan ahead to determine which is the next room you want to explore in order to achieve the final goal. Okay, so this is basically we are using a house 3D environment, which is our previous work that turn an 45K scene into an environment so that the agent can move around. So each scene is basically designed by humans, so they are more natural than a random generated maze. So you basically use that environment to basically to train the model. The first you can learn like the prior between different rooms. Maybe dining room is much closer to the kitchen, but less closer to outdoor, etc. Right? And then you can basically train it. You can basically test in a new environment you have never seen before, and we see that there is improvements in comparison with the random exploration, or you use a simple model-free approach. So the improvement is quite big when the optimal plan is actually long. So if you want to go across the entire building to the another room, then planning becomes much more important. Okay, so here's one case study, and I will skip that because of time. So basically the idea is you first try different paths. The first path is to go directly to the outdoor, but that fails. So then you update your belief, and then you try different paths until you find the right path, which is going through the living room to the outdoor, which is the right path you can go. Okay. Another work that I want to introduce is how can we use reinforcement learning to improve any existing plans. So for example, in this figure, we basically show here's one trajectory, that is your plan to destination. But after that, we can actually make the plan better by moving all these nodes around so that the overall cost is smaller. So if you are dealing with a continuous control problem, then usually people already developed a lot of very strong mathematical tools to solve this problem. For example, iterative LQR. So in that case, what you do is you locally expand the dynamic model that you have, as well as your reward model you have, into a local linear, local quadratic forms. And you use these two, you can basically run an LQR, which has the closed form solution. So once you have this LQR, you can update all the nodes, all the states there, and to improve your plan. And then once you get a new policy, you can sample the policy, you get a new trajectory, and you iterate. Right? But however, what happens if you don't have a good plan? What happens if the plan is not differentiable? So this is actually very, very common in combinatorial optimization. Right? So if you have, for example, you have 4 points, and you want to use these 4 points, you want to find a convex hull of it. Right? So a previous work for example, this is from DeepMind. This is from Google Brain. They basically try to predict the convex hull by a sequence-to-sequence model, which is used in a language model. Right? So there's another work that is recently published that basically uses a neural network to directly predict a plan for job scheduling. So here, we are trying to think about a different way of solving this problem by iteratively improving the solution in a local manner. So every time you basically pick a local part of your current state. For example, here's a job scheduling problem. So you're starting from like a state, and you find a region you want to improve, and then you use a neural network to find a good solution to improve it, and you get a better job scheduling. We actually get a better performance compared to a few different heuristics. For example, you shortest job first, and also heuristic plus search. Right? And also, our approach is better compared to other approaches that directly predict the entire plan. So when the solution is more complicated, directly predicting the right plan may be very hard. But our approach can gradually improve the performance. Okay, so we also apply the same thing for expression simplification, and we get a good performance. So here's one example. So I think there's a lot of future directions that we are thinking about, including hierarchical reinforcement learning, multi-agent, and also maybe model-based reinforcement learning, which we actually had a submission, but we haven't, which we will omit in this talk due to the time limitation. And I think the final slide is about people who want to work on reinforcement learning. How can we do well in reinforcement learning? There's a few requirements. You need to have very strong math skills. You need to have parameter tuning skills. And you have experience on C++, on distributed system. And you also have very strong coding skills. That's my talk. Thanks.
Thank you. We still have time for a couple questions. And put up your hand. Our volunteer will come by.
Thank you. It's a great talk. So for reinforcement learning, I mean, sometimes it requires a lot of computing resources, such as thousands of GPUs. I mean, for Facebook or Google, it's definitely not a problem. But do you have any suggestions for smaller, I mean, research groups who may not have this kind of computing resources to conduct research in reinforcement learning? Thank you.
Okay, I think the question is very practical, right? So one thing we could do is we can start from human demonstrations, right? So if you already have human demonstrations, then it will be much easier to train an initial model, and you can basically use reinforcement to improve on top of that. So this is something that you can do. And the other thing that you can do is, for example, if you want to you learn a model, as I mentioned in talk, once you learn the model, then you can basically do imaginary rollouts. You try to imagine with the model rather than running the actual simulator. That usually will be much faster. So there are several ways you can think about that. Right.
Next question.
Thank you. Nice talk. I'm Jackie from Sony PlayStation. So we are encounter some problem we need to solve. That now those algorithms try to train the agent to be very good at the game planning, but is it possible to train the model say, okay, that the player play the game more enjoyable? For example, if you have a top-come corner, it's a true story. So a friend of mine bought a chess game for her daughter, for his daughter, and she played it like 3 times because she got beaten because the AI is pretty good.
Okay.
So it's possible that there's a model that maybe personalized. Say, okay, I have the same label, so I have a component with my same label. It's possible to doing that kind of agent.
Yeah, I think it's totally possible. I think it all depends on how you design the reward, right? So the reward is good collaboration with the human. Then I mean the agent will try to find the good strategies that collaborate with human. So it do depends. For example, for Go, because the final reward is whether or not you want to win the game. So they will become very strong after you have trained it, right? So, but if the goal is different, then it will be steered to a different situations. You can also start from imitation learning, in which you already have a human trajectory, and you require that reinforcement agent is not deviate too much from the trajectory. That may give you a reasonable policy rather than a very wide policy there. Or you can put a handicap for computers, right? So whenever you mine a mirror, I mean, you get 1 point, and the computer don't get 0.5. This is also one way you can balance the two.
I think we're out of time. Let's thank our speaker.
Okay, thanks.